In this video, I'd like to discuss the inverse Laplace transform. Now, notationally, if the Laplace transform of little f of t is big F of s, we will refer to little f as the inverse Laplace transform of big F. And notationally, we say L inverse of big F is equal to little f of t. And because the inverse Laplace transform is simply undoing the Laplace transform, much like an antiderivative undoes a derivative, for every formula we have for the Laplace transform, there is a corresponding formula for the inverse Laplace transform. The most common formulas that we see, at least initially, are the four that we have written down here. The inverse formula is corresponding to t to a power, an exponential, a cosine, and a sine. So let's look at a few common examples and see the standard algebraic manipulations that will be required. When it comes to evaluating inverse Laplace transforms, I usually describe it as being a two-part process. First is the pattern recognition, which formula are we going to use? And then it becomes algebraic manipulation. How do we make it look precisely like that desired formula? So with the inverse transform of 2 over s to the fourth, let me just note to the side, this looks awfully similar to that formula corresponding to t to the n. So if it's n factorial over s to the n plus 1, we would get back just a t to the n. So in this case, we can clearly see in the bottom, we have 4 is equal to 3 plus 1, so our n value is 3. That means the number that we need in the top would be a 3 factorial, so it matches up precisely with this formula. So we manipulate now algebraically. To have a 3 factorial in the top, I need to multiply by 3. But if I'm going to multiply by an extra 3 in the top, I also need to multiply by a 3 in the bottom, so that we are simply multiplying by 1. Once we've done so, the 1/3 hangs around out front, and what we have is the inverse transform of 3 factorial over s to the fourth, which is 1/3 t cubed. Another very common type of problem encountered would be an inverse transform of the form that we see here. And the s squared plus 9 in the bottom from our extensive practice should indicate to us to think about the cosine of AT formula and the sine of AT formula. So with that in mind, let me just add a few formulas to the side here. The Laplace transform of cosine of AT is equal to s over s squared plus a squared. And the Laplace transform of sine of AT is a over s squared plus a squared. And then you can think about this intuitively for the inverse formula. If you had the inverse of s over s squared plus a squared, it's cosine of AT. The inverse Laplace transform of a over s squared plus a squared is sine of AT. For the given problem, we can break this fraction up over that addition in the numerator, so it's into 2 manageable pieces. So we can think of this as the inverse transform of s over s squared plus 9 plus the inverse transform of 1 over s squared plus 9. The first part looks identical to the cosine formula, where a squared is 9, so I'm going to just note here a equals 3. So this would just be cosine of 3t. Similarly, having a constant, there's a 1 I haven't written down here, over s squared plus 9 looks an awful lot like this sine formula, where once again a is equal to 3. But in order to match it up precisely with that formula, we don't want a 1 in the numerator, we need a 3. And if we put a 3 in the top, we also need to balance that out with a 3 in the bottom. So this would be plus 1/3 sine of 3t. And if we are thinking of seeing this as the last step of solving an initial value problem, we could certainly expect to frequently encounter quantities such as these as solutions of a constant coefficient differential equation. One more example involving some very typical algebraic manipulations with calculating inverse transforms. When we see something of the form given here, this s times s squared plus 4 product in the denominator indicates that we will need to do a partial fraction decomposition. The idea being, if I could instead have the inverse transform of some number over s plus some number over s squared plus 4. Then I would note that the first one is going to be a formula we know, and then the second one is also going to be a formula that we know. So we just need to take care of that partial fraction decomposition. And this is something we can just find to the side. 1 over s squared plus 4 is going to have this form a over s plus bs plus c over s squared plus 4. So clearing fractions, we would have the s terms cancel in the first piece, so just a times s squared plus 4. And the s squared plus 4's cancel in the second term. And at this point, we can always substitute in, because we have a linear term here, an intelligent choice of s that immediately allows us to solve for one of these. So let me just note kind of to the side here, if s happens to be equal to 0, we have 1 on the left and 4a on the right, so a is 1/4. And that might help us out in a bit. To solve for the other two, we need to expand everything out in equate-like terms. So if we imagined distributing out the a, distributing the s, and combining terms, we have an a plus b s squared plus cs plus 4a. And then the coefficients on both sides have to match up. There is no s squared term on the left, so a plus b has to equal 0. There is no s term on the left, so c on the right has to be equal to 0. Because a is 1/4, b is minus 1/4. So our partial fraction decomposition is we can rewrite the function whose inverse Laplace transform we would like to find as a over s plus bs plus c over s squared plus 4. c is 0, so we have a minus 1/4 s over s squared plus 4. So if we break this up and pull out constants, we have 1/4 the inverse Laplace transform of 1 over s minus 1/4 the inverse Laplace transform of s over s squared plus 4. The first inverse Laplace transform note is just equal to 1. And the second one is the cosine of AT formula, where a is equal to 2. So this would be minus 1/4 cosine of 2t.